Okay, good morning. Our next speaker is our colleague Boyan Sirakov here from PUC. He's going to talk here, Boyan.
Yeah.
He's going to talk about uniform or not a priori estimates for the Lane-Emden system in 2 dimensions.
Thank you, Nico. Wow, thank you. You almost sang my talk. Yeah, so, okay, we are here to say happy birthday to Carlos. And most of us maybe should even say thank you for so many things. I've been working in Rio for 13 years now, and certainly wouldn't have happened had it not been for Carlos. And I'm very happy that he gave me that idea and helped me come. And also our department's has been taking so much advantage of what he's doing, and simply from his heart of gold. You know, students, he has been the advisor of many students, but even the mentor of so many more. And I think we really care a lot about that. So it's a special opportunity to thank Carlos. Yep. So now, well, I realized that this meeting is a pretty diverse one, and topics are varied, and actually only Carlos is able to understand everything that's being said. So, yeah, so I chose a topic here that's at least easy to present, so for at least a good part of it, probably everybody will be at least able to understand what's it about. And, well, it's about a simple nonlinear elliptic PDE. Well, simple looking, I mean, not simple per se. And the so-called Lane-Emden equation and generalization of it to a case of a system of 2 equations. So let me start just, okay, it's not about applications at all, this talk, but just noting that it's been around for more than 1 century already. First time it was written in the form it is in a book by a physicist Lane-Emden in 1907. And the equation is the following simple thing, right? It's the diffusion operator, and we have a power of the unknown function. And usually, and in this talk in any case, we'll be interested in positive solutions. And here U is some functions defined on a subset of a Euclidean space of any dimension. For now, well, as you see here, it appeared as a model in astrophysics in a situation where there is what they call the polytropic fluid, which is essentially meaning that the volume is proportional to density to a power. Okay, so this U here is like a power of the density or a power of the pressure. Okay, spherically symmetric self-rotating fluid.
P is fixed and greater than 1.
P is fixed and greater than 1. You're right, and P is what they call polytropic index. And actually, this talk will be about an asymptotical regime of P, which makes sense. P goes to infinity. But yeah, various values of P mean things. Well, I mean, since the 60s, there's been this equation actually is being used as a standard example of a semilinear elliptic PDE, right? Because of its form, I mean, it's really a diffusion and a nonlinear dependence in the unknown function. And that dependence is simply a power here, okay? I mean, Charles Epstein here yesterday talked about the years 70s and 80s in current when people cared about nonlinear equations and despised linear ones. I mean, this was one of the examples of things they would care about at that time. And yeah, so, well, that's what we're looking at. Well, so once more, this is the problem. Here we'll be using, we'll be coupling that with a Dirichlet boundary condition in a smooth bounded domain in the Euclidean space, right? So before moving to the main topic of my talk, I want to review a little bit properties of that thing and also just give some context to help understand how people and what people have looked at. So to start with, it has a variation of structure. This means it is the Euler-Lagrange equation of a given energy functional, which is actually pretty simple to write. Yeah, this it's a Dirichlet. N is the dimension. N is the dimension. P is the exponent. Yeah. So N is dimension. Yeah. Little n. Yeah. Little n, because there will be a capital N, which will be something else. So yeah, given that function over here, I mean, this is and there's a special exponent, this number I call P star, which is defined only for dimension bigger or equal than 3, and it is actually what? Here we have a Dirichlet energy, and here we have some LP norm to a power of the function. So if P, this parameter is smaller than this P star, then this term here is essentially controlled by that term. I mean, of course, if we take just norms, not as it is, but which means that if P is more than P star, then solutions of that equations are also critical points of that functional, defined, for instance, on the Sobolev space H10, so functions that have square integrable gradients. And so under P smaller than P star, actually this is simply well defined on that space. And for P bigger than or equal than P star is not well defined on that space. Since the LP plus 1, the Lebesgue space AP plus 1 might not be embedded in H1. Well, also another way of seeing solutions of that, after a normalization, they can also be seen at constrained critical points of the Dirichlet energy, the pure Dirichlet energy, on the unitary sphere of the Lebesgue space. Yeah, actually, if it is on the unitary sphere, we'll get actually sign-changing solutions. I should take this integral equal to 1 to get the positive solutions. But it's also it's also a sort of a constrained critical points on a manifold. Okay. And well, and note that in 2 dimensions there's no restriction on the exponent. And actually, this talk will be essentially 2 dimensions. Well, a few among so many results about this sort of equation, that equation. Let me review a few. Now, so first. A result by Pokhuzaev in 1965 already established that if P is bigger or equal than this critical exponent, and the domain omega has sufficiently simple geometry, say star, which means that there's one point from which we can see all the domain, right? There's one point in the domain such that for all other points the segment between the 2 is in the domain. Then actually there are no solutions of that equation, essentially meaning that this restriction coming from the variation of formulations on the previous size is not something technical, but rather really inherent to the problem. And a very classical theorem of Brusetti and Rabinovich in 1974 establishes that actually if P is smaller than the critical exponent, n plus 2 over n minus 2, or which means for any P if n is equal to 2, there is indeed a solution of that problem. That was related to what people would call at the time the mountain pass theorem. So there's a result which essentially is a way of founding a critical point of a functional on an infinite dimensional Banach space. Well, further, a result by Giddens-Sprague in 1981 establishes the following, that actually we can say that solutions a priori are bounded for values of P smaller than the critical exponent, which, I mean, we don't know how many solutions are a priori, but certainly we know that they're in a fixed ball in L infinity or even in C infinity by regularity. So there is a constant depending on P and on the domain, such that any possible solution of that problem is bounded by that constant. Okay? This will be an important result for us. Okay, actually this result also implies the previous result through a different technique related to degree theory. Also, we can use that thing here to prove the second theorem, different way, through degree index theory. And let me just note that for that simple looking equation, it is still an open problem that for simple domains, even for convex domains, solution is unique. People believe it is unique in a convex domain. And except in particular cases that I'm going to probably review quickly, we do not know that. Right? The reason being that solutions of this equation are essentially unstable critical points. There is a negative subspace. I mean, they are not minima. And it's difficult to prove uniqueness in that situation. So, in any dimension. Even in dimension equal to 2. We do not know that the solution of that is unique, except in particular cases that actually I'm going to review. But one particular case for which we know it is if this is a ball, because then we actually know that solution is a radial. And so it becomes an ordinary differential equation, and we can prove, then there is a way to prove uniqueness. But apart from that, it's still open. Apart from that, such a basic question is still open. Okay. So move on. Once more, the result by Giddens and Sprague. And, well, a natural question that appears here in that situation is what's happening if that exponent P gets close to the critical exponent? Okay. So what's happening if P is smaller but goes to P star? What happens with this bound? Well, I mean, this has been a subject of many studies. Well, one obvious thing is that, for instance, in cases when we have omega has sufficiently simple geometry, such as star-shaped, and P and this dimension is bigger or equal to 3, so that this is well defined, the constant has to go to infinity. This C here, I mean the optimal constant, has to go to infinity, simply because if it were bounded along some subsequence, there would be a sequence of solutions that are uniformly bounded in P, and by regularity we would be able to construct a solution for P equal to P star, and there is this result that I quoted, which says that there are no such solutions.
So, but this result, it gives no formula for C, it just it exists.
No, there's no formula.
No estimate, nothing.
There are the estimates there. They are raw estimates, yes. They are raw estimates. On the other hand, this argument, which I just presented, very simple argument for that, it doesn't work for n equal to 2, there's no limitation, and so question, what's happening if P goes to infinity and dimension is 2? Okay, so that's first question we are looking at. And let me tell you, now, so the first reaction one may have is probably that C would go to infinity again as P goes to infinity. Now, a result of already 30 years ago by Ren and Yunchen Wei tells us that actually this is not true, at least for a particular class of solutions. Least energy solutions. Remember that moment I said that solutions can be seen as critical points of Dirichlet energy on a manifold. So solutions that have least energy actually are uniformly bounded as P goes to infinity. That is, there is a bound in P2, which makes the case n equal to 2 very different from the case n bigger or equal to 3. Right? Actually, there's a reason for that. Actually, there are some estimates that can be written, and these estimates hinge on the fact that we have the following bound that can be established not very difficultly from the fact that the energy is minimal, is that actually the Dirichlet energy goes to 0 at least like 1 over p as p goes to infinity of any solution at level for any p. So when p goes to infinity, we have this bound. And it's been an object of interest to understand more about the asymptotics of solutions, maybe least energy solutions, or even better if possible, any kind of solutions, as p goes to infinity. That's been, and actually this, we arrived at a pretty good understanding of asymptotics as p goes to infinity of solutions, maybe about 10 years ago, in particular due to those authors here, mostly Italian mathematicians. And I've gathered here a few results about the asymptotics of solutions as p goes to infinity of our Lane-Emden equations. So essentially, gathering a few results, we have the following. If we know, this is a condition, this is a hypothesis, if we know that this is true, then we can quite well describe asymptotics as p goes to infinity. So it is true that there is a finite set of points in the domain omega, which we can determine exactly through an electrostatic kind of condition, that is, it is determined through the regular part of the green function of the Laplacian. There's a way to determine where these points are. And in the particular case when the domain is convex, for instance, there's only one such point. And it is such that this set of points is such that the solutions go to 0 away from these points, at least like 1 over square root of p. The maxima of solutions does not go to infinity, does not go to 0, it goes to a specific constant, which is square root of e. So actually at the point, at least the maximum is somewhere close to these points, and it is like square root of e. The energy quantizes, which means that p times the energy of any sequence of solutions goes to k times this constant here, a times pi e, as p goes to infinity. Rescalings of solutions tend to, this in a sense one could imagine why, tend to the entire solution of the so-called Liouville equation, right? It's a logarithmic function, right? It's essentially a logarithm here. And another interesting property is that at least for large p, we can deduce that solutions have Morse index exactly 1. I mean, this means that the linearized operator of the Laplacian of u plus pu p minus 1 has only one negative eigenvalue, right? The negative subspace is of dimension 1. So it's unstable, but as little as stable as possible when p is large enough. This is a few properties that people were able to establish at for p goes to infinity. And there was that hypothesis here, right? Which actually I learned about these problems when Filomena Pacella, some of them was giving talks and was giving, actually this was an open question. Is it true that this is true? Is it a fact that this is true not just for least energy solutions, but for any positive solution, for any solution of the Lane-Emden equation? So that was the thing we looked at with Nicola Camburov from Universidad de Chile a few years ago. And it's indeed related to the fact that solutions are uniformly bounded in P2 when P goes to infinity. And we managed to prove that indeed solutions are uniformly bounded, not just least energy, but all solutions are uniformly bounded. I mean, as P goes to infinity. P, of course, has to be away from 1 because at P equal to 1, this is an eigenvalue problem. But as P goes to infinity, solutions are uniformly bounded in P2. And through what's called the Pokhozaev identity, this implies indeed that if the domain is star-shaped, then this is what I call this IB, integral bound. Yeah, I didn't say, but I use this, yeah. For instance, IB is integral bound, LE is Lane-Emden, and the little e is equation, because there will be a system later. Yeah, so we have the integral bound. So actually this theorem, this set of results here is proved to hold without restriction for all solutions of the Lane-Emden equation. IBE holds always in a star domain. Okay. Right. Okay. So yeah, that's this the next slide here. IB is always true in a star-shaped domain. So by the results I quoted, all the asymptotics is valid for arbitrary positive solutions and not just least energy. Or if you like speaking of energy, the asymptotics holds at all energy levels, not just
uniqueness then in this context.
Well, you would hope we don't know. Yeah, I mean, essentially, if the uniqueness were true, we'd know that there's only one solution. So.
Sorry, I thought that K, we would have K equals 1.
No, K is a point in the set.
Yeah.
K is a point where solutions attain maximum, around which point solutions attain. It doesn't mean anything about uniqueness of solutions.
Right, so there could be different points in the domain.
Yeah, there may be different even subsequences. For instance, one subsequence here, one there. There's no reason to think. I mean, that doesn't imply actually we believe there's uniqueness, at least for. And yeah. And actually, this last result over here does imply uniqueness. That's what I was going to say. I was going to observe now.
Is K equal 1 in the star-shaped domain case?
We don't know. I'm not sure they know it. No, I think it's proven only for convex. It should be. I mean, but yeah. So yeah, we know it's K equal 1. We know it only for convex. Yeah. Okay. Yeah. So precisely about uniqueness, this implies something about uniqueness because we know it's a result by C.S. Lin in 1904 that actually Morse index 1 solutions are unique. There's only one of them. I mean, there's only one solution that has Morse index 1. The solution that comes as minimizer is the only one that has Morse index 1. And so this implies, by the fact that all solutions were proven to have Morse index 1 for big P, that actually for P sufficiently large, solutions are unique in a two-dimensional convex domain. So this creates a pretty weird situation in the sense that now this is a very strong evidence that the conjecture of uniqueness of positive solutions in a convex domain is true. Because we also know we have a perturbative result, again by C.S. Lin, that says that uniqueness is also true for small p equals to 1. So now we know that for p equals to 1 in a two-dimensional convex domain, solutions are unique, and also for p large enough. One would doubt that in between uniqueness will hold too, but even that we do not know. So that's the state of the art. I mean, at 2 dimensions at least we know that for big P is uniqueness valid. Okay. Yeah. So now I would like to switch to another model. It's what we call the Lane-Emden system. And it's the following object here. So now we have 2 equations. And the thing is that there's a coupling, right? It's a fully coupled system. So we have two functions, 2 diffusions. And we have dependence. A portion of u is v to a power, and a portion of v is u to a power. Right? Again, take p and q bigger than 1 at least, say, and look at positive solutions in some bounded domain under a Dirichlet condition. Right, so let's look at this. First thing First thing I want to observe is that if P is equal to Q, then U has to be equal to V. This is a simple consequence of the maximum principle. Yeah, so P equal to Q actually reduces to the equation that we had before. Right, so this is, if P is equal to Q, we get the Lane-Emden equation. Now, again, that thing over here is an example is a simply working example of a system that's Euler-Lagrange for energy functional. Well, what's that function? Here it is. Okay, we still have these terms that are some P plus 1 or Q plus 1 norms in Lebesgue spaces. And we have here is the energy term. And now look, it's pretty harder than what we had for one equation. Of course, if P is equal to Q, U is equal to V, so this is the usual Dirichlet energy, and we get the function we had before. But now this thing is not positive. It's even actually strongly indefinite. On one diagonal of the space H1 square, on one diagonal this is positive, on another diagonal this is negative. So it's a strongly indefinite functional. Still, people were able to find ways of looking for critical points of such objects, and implying thus existence of solution to this system. Let me review a few results on that. Okay, here. So yeah, I think it's pretty clear what I'm saying here, right? Yeah. So now let's compare to the case P equal to Q. We had that critical exponent. Remember that n plus 2 over n minus 2. That essentially was saying that we could define well our functional on a good Sobolev space. So here again there is a dividing line for P and Q. So in the P and Q space, actually the dividing line is a hyperbola, right? Which is the following thing. If that is true, if that thing is here is true, then the functional we had here can be well defined on some product of Sobolev spaces. Right, this is, with equality here is what people call the critical hyperbola. Again, if P is equal to Q, this reduces to P is more than n plus 2 over n minus 2. And well, actually, a better way of writing this here is the sum of these two being bigger than n minus 2. Why is it better? Because these are the natural scaling exponents related to this. What I'm saying is that if we take this problem in RSA and we take a dilation of the space with some parameter lambda, we have to multiply U and V by lambda to this power and lambda to this power in order to keep this invariant. So it's essentially these are scaling exponents, and the alpha and beta I'm going to call them. And so the critical hyperbola will be denoted by alpha plus beta bigger than n minus 2. And again, of course, this is a void hypothesis if n is equal to 2. And one may ask the following question. So if n is equal to 2, will solutions be uniformly bounded as P goes to infinity and or Q goes to infinity? These types of problem have, essentially, we have believed that, okay, systems of this sort, they have a much more complex structure than just one equation, all right? But still working harder, doing harder stuff, we get to prove essentially similar things for systems as for scalar equations. So probably one of the main points of this talk is that we are going to see an instance, which to me is the first instance of that sort, where something different will happen for the system compared to the scalar equation. It's a sort of an unexpected phenomenon. So actually, it turns out that the answering this question is not easy. We have only partial answers, and some of them are quite unexpected. All right, See, the point is that there is this and or here, right? I mean, P goes to infinity and or goes to infinity. I mean, they can go to infinity together at different rates. One can go, the other not, and so on. And this might matter. But okay, let me review a few results on this theory here. So, which are extensions of those that I quoted about scalar equations. So first, if P and Q are above or on the hyperbola and the domain is star, there are no solutions. Similar, yeah. So above the hyperbola, no solutions. Below the hyperbola, result by Rabinovich in 78, this is the Rabinovich linking theorem, that says that below the hyperbola, there exists a solution. Of course, uniqueness is open, since uniqueness is open even for P equal to Q. So it's even more open for systems. Right, but so non-existence and existence essentially go over to systems as the way one would expect. Now, when we go to a priori bounds, things get harder. So what we know about boundedness, uniform boundedness of solutions of this, for every fixed P and Q. Actually, there is not a full picture. We don't have that result that I have for P equal to Q that was saying, okay, if solutions exist, they are a priori uniformly bounded. Here I'm at fixed P and Q. I'm not interested yet at asymptotic regimes of P and Q. I'm just fixing P and Q. I'm speaking of boundedness of the set of solutions. We know that solutions are bounded in quite a lot of cases, but not all. So if P and Q are under the hyperbola, and dimension is more or equal to 4, that's the best we know, or under some additional hypothesis, which is actually say, one of them is saying that this sum is not bigger than n plus n minus 2, but actually each one of alpha and beta are bigger than half of it. That works. And also if one of them is bigger than n minus 3, then it works too. But in general, this is still open. And this is related to actually another open problem that's been driving people crazy that work on these sort of problems, the so-called Lane-Emden conjecture, which is essentially a result on this system, but set in the whole space in Rn. And we expect to be able to know that actually below the hyperbola, if the problem is set in Rn, positive solutions do not exist. There's a method, this is the Giddens-Pratt method, which actually says that if this hypothesis, if this conjecture here is true, then this would be settled for. I mean, whenever we are able to prove this, we are able to prove a bound like that.
Positive in Rn means positive in all of Rn.
Yeah, defined in ORN, entire. Defined in ORN. Because here, most of the results that I'm quoting here are about the bounded domain. Yeah. So there's a sort of duality. When there are solutions in a bounded domain, there are no solutions in Rn and vice versa. It's a pretty, curious occurrence. Actually this, the non-existence in Rn under the hyperbola is still open. Precisely what we know is that there are no solutions in Rn if these things here are true. But, for instance, in n smaller or equal than 4, what I'm talking here is essentially n equal to 2. So this is, but I'm just reviewing a few of the outstanding results in the theory. All right. Of course, n equal to 2 is everything is void. Yeah, so fine. That's one open problem here too. That's been studied a lot, and yet we are essentially at these hypotheses for the Lane-Emden conjecture. Right. Okay. Okay, let me move now to again. So I'll move again to 2 dimensions. And the question in 2 dimensions will be again what's happening with this C here when P and Q go to infinity. Okay. Well, yeah, a few years ago there was a work by Chen Li and Wenmin Zhu. This is Wenmin Zhu, these mathematicians from Tsinghua University, who proved that for the system, if P and Q go to infinity, and they are essentially very close, I mean, the distance between them is finite, but still they are different. I mean, the system, we are really in the system case. I mean, then all the asymptotics, uniqueness, and so on can be extended to this system, provided, again, there is an integral bound that is required, and this is the same integral bound. I mean, not the same, but the integral bound that extends the one before. So we want that integral of this scalar product be like 1 over P, for P going to infinity and Q staying with P. Right. And well, so obviously we wanted to see if this can be removed, in the sense if this is true for all solutions, just like I showed for one equation. Okay. Okay, so yeah, I'm here reviewing again what I said once more. Yeah, this slide is probably redundant. I already said that this reduces to the equation case for P equal to Q, that there is a fundamental difference for P different than Q, and so on. Yeah, we wanted to see that that previous work we did, that work I quoted already with Nikola Kamburov, can be extended to systems, and see that in 2 dimensions as P Q goes to infinity, solutions stay bounded. And also if there's a way to prove that bound, which actually is very different in the systems case, because the proof that we knew for one equation did use that this was a positive thing and there was a Cauchy inequality to be used. Okay, so how am I faring on time-wise? Obviously, I don't think that I should spend too much time on proofs, but I'll just review a little bit of the proof of what we could do actually to prove a priori bounds for, uniform bounds, both in PQ as PQ goes to infinity for solutions of that thing over here. Well, just to give an idea. So how does what we did proceeds? Well, we have that our system, Dirichlet condition, positive solutions, and so on. Say U attains the maximum at some point xu, V attains the maximum at some point xv. Call these things M and N, right? This M and N. Let's remember at least this notation M and N, which will be M will be the maximum of the U component, N will be the maximum of the V component. And now, well, we know a lot of things. There's a method called the method of moving planes. These are not planes that move in the skies. I mean, it's a method of reflection with respect to hyperplanes that let us prove that maxima are attained uniformly away from the boundary. And then there are various facts that one can establish. First, it's not very difficult to prove that the L1 norms of the right-hand sides are uniformly bounded in P and Q. Then we have obviously L infinity estimates for the Dirichlet problem, which directly says that M is smaller than NP, N is smaller than NQ. Then here it gets more delicate. Now, writing the equation for M minus U, N minus V, and applying the inhomogeneous Harnack inequality at points where these things are 0, we get bounds of the sort of M minus U. Here we are estimating how U goes away from their maximum in V. And the Harnack inequality says that we get from the equations precisely things like this, with a power R square, where R is any radius such that 2 times R is still in the domain. This is the Harnack inequality with the right-hand side. applied to this thing. Just apply Carnot to n minus u and n minus v. At a point, I mean, using the fact that the infimum of this is 0 at the maximum points, x, u, and x, v. And so now we can take R at least that much by these bounds, because for sure we are still inside the domain for such R's. And plugging this R here, actually this gives you a bound which is like u is still bigger than 1 minus 1 over q in both of that size. These both, they have very small size, but we get that. And this gives you that u to the q is bounded below by still positive constant, its maximum to the q, in these very, very small balls. This comes from Harnack. And then, now we write the green formula at points of maxima. Now the regular part of the green function is bounded because of the bounds we had before. And the point is that there's a logarithm. And okay, playing with these logarithms in the green function, we essentially get horrible looking things like this. You don't need to read it, but we get some bounds on m and n that we still are unable to uncouple. But since we had an integral bound, using again this in the integral bounds, we get some different comparisons between the maxima. And here actually come these q over p and p over q that matter. And now this, together with that, lets us uncouple a little bit. And we get this much better looking the relations between m and n. And multiplying them, we get the essential bound, which is that. We can always prove that log of the maximum of u times log of the maximum of v is uniformly bounded in p and q. Of course, this doesn't mean that each one of them is bounded, since simply one of them can go to 1 and the other can go to infinity in this product of logs. Yeah, so it only tells us what we want if m is bounded if n is away from 1, and n is bounded if m is away from 1. Of course, if we had one equation, we are done at this point because m is n. And so, and now from these bounds, we already can see that if p over q is bounded, then this n over this thing here is this power is bounded, and so m is smaller than a power of n, fixed power of n. And now we are okay with m because either n is bounded, and then m is bounded, or n is unbounded, but then it is bigger than 1, and then m is bounded. So if p is smaller than a constant times q, m is bounded. And if q is smaller than a constant times p, analogously, n is bounded, which is what we wanted. And we prove the theorem here, which says that, okay, if p is controlled by q, then the u component is uniformly bounded. And if q is controlled by p, then the v component is uniformly bounded of our system. Which means that if p is comparable to q, in the sense that p over q is bounded above and below by positive constants, then we have the desired bound on both, right? So if p and q are, well, of course, I mean, in view of the applications, to that asymptotics and uniqueness results that I quoted, this is more than enough, because at least for the asymptotics that we know up to now, because they were proved under hypotheses like that, which is way worse than this thing, of course. So for the applications, this is enough at this stage. Yeah, so we have all these asymptotics and uniqueness under that hypothesis here for all energy levels, again, just like that we had for one equation. But obviously, I mean, this hypothesis here is a little bit underwhelming at the first glance. Why should p and q be comparable, right? To have for the system what we had for the scalar equation. Okay, yeah. So I think I'm not going to show you I don't know if I'm going to bother you with the. Well, just maybe mentioning here that the integral bound, the fact that this thing here behaves like 1 over p and 1 over q, well, it proceeds, how does it proceed? multiply one by V, the other by U, use the fact that V and U are bounded to have bounds of these things in terms of L1 norms of right-hand sides. Then use Pokužajev identity. Pokužajev identity for a system says things like that. So actually we relate 1 over Q to U to the Q plus 1 to product of the normal derivatives of the boundary. And there is this thing here, which is the reason for which we know to do things only in star-shaped domains, because we want this to be positive, x times the normal derivative. Maybe that's the reason. That's the Pokužajev identity, and the fact that this term appears here is the reasons we need star-shapedness for some of the results. We want this to be positive. Well, and then if again P and Q are comparable, and if we are able to prove that from BO this is bounded by the right-hand sides, integrals of right-hand sides, then essentially this will lead to what we want. Let me not enter in details, but the thing is that actually this bound on normal derivatives on the boundary is not something very obvious. And it was actually pretty cool when you have done something, and even recently, in a completely different, ideas and different type of problem, and it enters like that to help you prove something you want in a quite a different looking work. So a few years ago, I actually was looking at an extension of the so-called Moser, the Georgi-Moser-Harnack inequality, up to boundaries. I mean, so the Moser-Harnack inequality is an interior result, and here it is. The classical, extremely fundamental result of the Georgian Moser tells you that if we have a superharmonic positive function, then for any compact subset and any exponents more than n over n minus 2, minimum of a superharmonic function is controlled from below by Lebesgue norm up to this exponent. Right? This is a quantification of the strong maximum principle, what people also call a growth lemma. And we can extend that up to the boundary, so essentially removing the compactness here. Then we need to replace u by u over the distance to the boundary, which makes here the normal derivative at the boundary. And the Lebesgue exponent can go up to n over n minus 1. And this result is actually relates also to results from potential theory, the so-called Hermitage theorem, which says that a positive superharmonic function is always at any Lebesgue space. Just the superharmonicity tells you that up to the boundary, the function is integrable up to order n over n minus 1, minus any epsilon. And the Hopf lemma, essentially, this thing is quantified by that thing in the two directions. But it turns out that this bound on the normal derivative on the boundary is exactly what we want to prove the thing that we needed here. So that's a pretty cool moment here. But well, let me move now to a consideration related to this frustrating hypothesis, P is equivalent to Q in the a priori bound. So now, okay, we proved that if P is comparable to Q, then we have the bounds, we have the uniform bounds, right? And well, question is this really necessary, or was it just because we didn't know how to prove how to make the proof work without it? Well, and actually, we were absolutely sure that this is technical and due to our being unable to find a better proof. Yeah, again, by this meta theorem that the subcritical system should behave like the subcritical equation in a sense. Subcritical means P and Q below that critical exponent. The result for the proof, the result for the system may be harder to prove, but there should be one. So, wow, try, no luck. And then one starts looking at particular cases. And obviously, a very obvious question was, okay, since we can't prove it in general, can't we go to a situation where we can actually go to an ODE? if we take the problem in a bow, then this becomes an ODE. We know by the theory of symmetry of solution tells us that if the domain is radial, if the domain is a bow, then solutions are necessarily the radial functions. So this becomes an ODE. This becomes a ODE system. So actually, the Lane-Emden system is the following system of two coupled ODEs, right? The radial Laplace plus these powers equal to 0 in the interval 0, 1. We have two positive solutions. We have positive solutions of that. They are strictly decreasing between 0 and 1. They have 0 derivatives at 0. They are 0 at 1. And what we care about is their values at 0. Just a super simple looking ODE system, right? And what we want to know is what are M and N as functions of P and Q, right? We want to know something about M and N as functions of P and Q. Well, here's the thing about us. Probably this, what's written here is due to the fact that we are not good at ODEs. But we did not find any way to actually exploit that system. So anyone being able to do something, yeah. So we thought, okay, let's do some numerics on that thing, right? Okay. Well, now, okay. So we want to look at situations where P is not comparable to Q. So let's take the worst possible case. One of them will be the smallest possible and fixed, and the other will go to infinity. And it's actually, this very particular case is actually interesting per se, because when P is equal to 1, look, this becomes Laplacian of U is V of Laplacian of V. This becomes square Laplacian, and it's the biharmonic Lane-Emden equation, which also matters. I mean, that's so. From this theorem, we already know that solutions of that equations are uniformly bounded. But what about the V component, which is the Laplacian of U here? Yeah, at least for numerics, taking one of the equations to be linear, it's nice, right? So here, what Maple, with our limited knowledge of it, told us. To start this, about the equation, just for P equal to Q, we see the following in a bowl. Actually, not just the maximum is bounded. Way more is true. The maximum seems to be decreasing and goes to that constant that appeared already at some point, square root of V, at least in a bowl, right? So actually, the theorem that we proved in any domain for that thing here, which is one of the proofs I started with, told us that the M as a function of P was bounded in P as P goes to infinity. Numerics actually tells us that at least in a bow, it seems to be actually a decreasing function and going to that thing that we know it goes to by the asymptotic analysis that's already been done. Right.
Where's the maximum achieved?
Oh, here it's in the center because the function is radial. Yeah. It's necessarily achieved at 0. I mean, it's at the origin.
Oh, it's right there.
Yeah. There's only one point of the maximum. The function is really a radial function like that. Okay, so now about the system. Well, starting with that, here's what we managed to see in the beginning. So here we have now the system, Q. M and N are the maximum of U and V components at 0. Again, they are radial functions, right? Again, they are radial functions. And see, the problem with numerics is that these powers are not great. I mean, if powers become too big, things break quickly, right? So in the beginning, we were able to compute this up to Q equal to 25. And then we saw exactly what one would saw in view of the simple equation is that both are decreasing. And this very strongly suggests that, again, our proof was actually incomplete. And boundedness should be true for any M and N, for any Q. Then one day, we tried again to prove the theorem, we couldn't. Then one day, we found a different procedure in Maple. which let us compute for larger Q. And we went to Q 140 and look the N. How about that? How would you have believed that the maximum in terms of Q has a minimum at Q about 29.3 here. And then it starts increasing. Yeah, so not quickly, but it increases. Yeah, so okay, now one starts doing another type of work. And here's a theorem we managed to prove, which is actually really a very strange looking stuff, right? So we are able to prove that in the unit disk, if P is 1 and Q goes to infinity, the N component, the V component, has a maximum which goes, this means its value at 0, goes to infinity like log of the power. Exactly log of the power. And that's, why is it log of the power? Yeah, but that's, yeah, I've already said, but it's a compelling piece of evidence that systems may have richer nature and greater complexity than equations, right? Not just more difficult to prove, but actually different properties. Right, so it's not bounded, and component is not bounded. It goes y log to the q. Yeah. Well, it's a harder proof. I mean, it's a harder theorem. So it uses heavier tools, like that global weak Harnack inequality I quoted. The Harnack inequality this time is even using unbounded right-hand sides. The so-called Bressis-Merrill L infinity estimate for the Poisson equation, which is like if you have a proportion of u equal to f, then integral of exponent of u over the maximum of f is bounded. And pretty fine estimates on level sets, actually. There's a sort of it's a little bit like in, we have estimates that sort of non-degeneracy way of u go away from its maximum, like a little bit like in free boundary theory. Yeah, and we do use for the wall bound. The wall bound is the hard bound, right? Where you prove that it does go to infinity, at least like logarithm. We use radial symmetry because we need to know that they both attain maximum at the same point and decrease away from it. In the proof is purely PD. We do not know how to use, we are in a bow, right? So there's an ODE also system, but we do not know an ODE proof of that. Well, and a few open problems, I mean, obvious open problems here. Can we prove at least that for any P and Q, the upper bound is always at least log PQ? It should be true since in the extreme cases it is true, but well, it's also open. Of course, essentially, most obvious question here is actually what is the optimal relation between P and Q which guarantees that both components are bounded? We proved it only on the fact that they are comparable. And we know only that it's false in a bow if one of them is the worst possible and P is just one. All in between. Where is the dividing line between this being true and being false in terms of P and Q? Yeah, and the lower log bound we have only for a bow. Is it true for general domains? And also the asymptotic and uniqueness for a little bit better than that thing here. It should be true at least for P comparable than Q. Okay, thank you so much and thank you, Carlos.
Exactly on time. So we have time for a few questions. Yes.
So do the results of the scale,
Go ahead, yeah.
Do you know if there's any relationship between the geometry of the boundary of omega and that number k, the number of...
Very nice question. I'm not sure. I'm not sure, but I don't think it's... I mean, there's a condition. I mean, these points, they essentially related to some min-max hypothesis of the green function.
Okay.
So there must be. I mean, from this you probably can infer something, but I'm not sure that I'm not sure that it's completely clear. Yeah.
That problem is begging for a numerical.
Absolutely, absolutely. I mean, it's just that someone who's good at numerics should do it. I mean. Yeah.
Boyan, in 2 dimensions, in the case of the disk, because everything is invariant under rotational symmetry, you can't say anything about uniqueness in that case?
Yes, we know the uniqueness in that case, precisely because we know that all solutions are radial. So all solutions are ODE solutions, and we are able to study the ODE to prove that solutions are unique. But even for the ODE, I mean, it's a non-trivial ODE result. That solution is unique. It's not something completely obvious to prove. Yeah.
Okay, more questions?
I think there's one here.
Yeah.
I have a perhaps very silly and basic question. In the very beginning, you started by giving a sort of a hint at a motivation from astrophysics for the equation. Do you know of any analogous motivation for the system?
Well, in the particular case when one of them is 1, yes, then there is the biharmonic one. Yeah, that's one situation where certainly this has a meaning. Now, for general values of the exponents, specifically this system is more like a model for things than anything else. But a little bit more complicated looking products of powers, which are generalizing this, are actually used in chemical reactions there. So so when you make it a little bit more complicated, it already becomes related to some models.
For the biharmonic case, what is the motivation? Is it also astrophysics? Or?
No. Then you know this it's this elasticity theory.
Oh.
Yeah, clamped plates and stuff. Yeah.
Do people ever think about geometric properties of the LP balls, which have to do with those strange phenomena?
I don't know if they think of it, probably, but how much is done, I'm not sure. but yeah, I'm not sure I can answer that.
Let's thank Boyan again.
Thank you.
Come back at 1:30.